Maglev is a method of propulsion that uses magnetic levitation to propel vehicles with magnets rather than with wheels, axles and bearings. With maglev, a vehicle is levitated a short distance away from a guideway using magnets to create both lift and thrust. High-speed maglev trains promise dramatic improvements for human travel if widespread adoption occurs. Maglev trains move more smoothly and somewhat more quietly than wheeled mass transit systems. Their non-reliance on traction and friction means that acceleration and deceleration can surpass that of wheeled transports, and they are unaffected by weather. The power needed for levitation is typically not a large percentage of the overall energy consumption. Most of the power is used to overcome our resistance, as with any other high-speed form of transport. Although conventional wheeled transportation can travel very quickly, a maglev system allows routine use of higher top speeds than does conventional rail, and it is this type which holds the speed record for rail transportation. Vacuum tube train systems might hypothetically allow maglev trains to attain speeds in a different order of magnitude. While no such tracks have been built commercially yet, there are efforts being made to study and develop super-maglev trains. Compared to conventional wheeled trains, differences in construction affect the economics of maglev trains. In wheeled trains at very high speeds, the wear and tear from friction along with the hammer effect from wheels on rails accelerates equipment deterioration and prevents mechanically based train systems from routinely achieving higher speeds. Conversely, maglev tracks have historically been found to be much more expensive to construct, but require less maintenance and have lower ongoing costs. Despite decades-long research and development, there are presently only 2 commercial maglev transport systems in operation, with 2 others under construction. In April 2004, Shanghai began commercial operations of the high-speed Transrapid system. In March 2005, Japan began operation of the relatively low-speed HSST Linamo line in time for the 2005 World Expo. In its first 3 months, the Linamo line carried over 10 million passengers. South Korea and the People's Republic of China are both building low-speed maglev lines of their own design, one in Beijing and the other at Seoul's Incheon Airport. Many maglev projects are controversial, and the technological potential, adoption prospects and economics of maglev systems have often been hotly debated. The Shanghai system has been accused of being a white elephant by critics and opponents. History. First patent. High-speed transportation patents were granted to various inventors throughout the world. Early United States patents for a linear motor-propelled train were awarded to the German inventor Alfred Sedan. The inventor was awarded U.S. Patent 782,312 and U.S. Patent RE 12,700. In 1907, another early electromagnetic transportation system was developed by F.S. Smith. A series of German patents for magnetic levitation trains propelled by linear motors were awarded to Hermann Kemper between 1937 and 1941. An early modern type of maglev train was described in U.S. Patent 3,158,765, Magnetic System of Transportation, by G. R. Polgreen. The first use of maglev in a United States patent was in Magnetic Levitation Guidance System by Canadian Patents and Development Limited. Development. In the late 1940s, the British electrical engineer Eric Laithwaite, a professor at Imperial College London, developed the first full-size working model of the linear induction motor. He became Professor of Heavy Electrical Engineering at Imperial College in 1964, where he continued his successful development of the linear motor. As the linear motor does not require physical contact between the vehicle and guideway, it became a common fixture on many advanced transportation systems being developed in the 1960s and 70s. Laithwaite himself joined development of one such project, the tracked hovercraft, although funding for this project was cancelled in 1973. The linear motor was naturally suited to use with maglev systems as well. In the early 1970s, Laithwaite discovered a new arrangement of magnets, magnetic river, that allowed a single linear motor to produce both lift as well as forward thrust, allowing a maglev system to be built with a single set of magnets. Working at the British Rail Research Division in Derby, along with teams at several civil engineering firms, the transverse flux system was developed into a working system. The first commercial maglev people mover was simply called maglev, and officially opened in 1984 near Birmingham, England. It operated on an elevated 600-metre section of monorail track between Birmingham International Airport and Birmingham International Railway Station, running at speeds up to 42 km/h. The system was eventually closed in 1995 due to reliability problems. New York, United States, 1968. In 1968, when he was delayed during rush hour traffic on the Thrugg's Neck Bridge, James Powell, a researcher at Brookhaven National Laboratory, thought of using magnetically levitated transportation to solve the traffic problem. Powell and a BNL colleague, Gordon Danby, jointly worked out a maglev concept using static magnets mounted on a moving vehicle to induce electrodynamic lifting and stabilizing forces in specially shaped loops on a guideway. Hamburg, Germany, 1979, Transrapid 05 was the first maglev train with link-stator propulsion licensed for passenger transportation. In 1979, a 908 AM track was opened in Hamburg for the first international transportation exhibition. There was so much interest that operations had to be extended 3 months after the exhibition finished, having carried more than 50,000 passengers. It was reassembled in Kassel in 1980. Birmingham, United Kingdom, 1984 Euro 1995. The world's first commercial automated maglev system was a low-speed maglev shuttle that ran from the airport terminal of Birmingham International Airport to the nearby Birmingham International Railway Station between 1984 and 1995. The length of the track was 600 meters, and trains flew at an altitude of 15 millimeters, levitated by electromagnets, and propelled with linear induction motors. It was in operation for nearly 11 years, but obsolescence problems with the electronic systems made it unreliable in its later years. One of the original cars is now on display at Rail World in Peterborough, together with the RTV-31 hover train vehicle. Several favourable conditions existed when the link was built. The British Rail Research vehicle was 3 tons and extension to the 8-ton vehicle was easy. Electrical power was easily available. The airport and rail buildings were suitable for terminal platforms. Only one crossing over a public road was required. No steep gradients were involved. Land was owned by the railway or airport. Local industries and councils were supportive. Some government finance was provided, and because of sharing work, the cost per organisation was low. After the original system closed in 1995, the original guideway lay dormant. The guideway was reused in 2003 when the replacement cable-hauled air rail link cable liner People Mover was opened. Emsland, Germany, 1984 Euro 2012. Transrapid, a German maglev company, had a test track in Emsland with a total length of 31.5 kilometers. The single-track line ran between Dar Paragraph Pen and Larthen with turning loops at each end. The trains regularly ran at up to 420 km/h. Paying passengers were carried as part of the testing process. The construction of the test facility began in 1980 and finished in 1984. In 2006, the Larthen maglev train accident occurred, killing 23 people, found to have been caused by human error in implementing safety checks. From 2006 no passengers were carried. At the end of 2011 the operation license expired and was not renewed, and in early 2012 permission was given for the demolition of facilities, including the track and factory. Japan, 1985 Euro. In Japan, there are 2 independently developed maglev trains. One is HSST by Japan Airlines and the other, which is more well known, is SC-maglev by the Central Japan Railway Company. The development of the latter started in 1969, and Miyazaki Test Track had regularly hit 517 km/h by 1979, but, after an accident that destroyed the train, a new design was decided upon. In Okazaki, Japan, the SC-maglev took a test ride at the Okazaki exhibition. Tests through the 1980s continued in Miyazaki before transferring a far larger and elaborate test track, 20 km long, in Yamanashi in 1997. Development of HSST started in 1974, based on technologies introduced from Germany. In Tsukuba, Japan, the HSST-03 wins popularity in spite of being 300 km/h at the Tsukuba World Exposition. In Saitama, Japan, the HSST-04-1 was revealed at the Saitama exhibition performed in Kumagaya. Its fastest recorded speed was 300 km/h. Vancouver, Canada, and Hamburg, Germany, 1986–1988. In Vancouver, Canada, the super-maglev was exhibited at Expo 86. Guests could ride the train along a short section of track at the fairgrounds. In Hamburg, Germany, the TR-07 was exhibited at the International Traffic Exhibition in 1988. Berlin, Germany, 1989–1991. In West Berlin, the M-Bahn was built in the late 1980s. It was a driverless maglev system with a 1.6 km track connecting 3 stations. Testing with passenger traffic started in August 1989, and regular operations started in July 1991. Although the line largely followed a new elevated alignment, it terminated at Gleisdreieck station, where it took over a platform that was then no longer in use. It was from a line that formerly ran to East Berlin. After the fall of the Berlin Wall, plans were set in motion to reconnect this line. Deconstruction of the M-Bahn line began only 2 months after regular service began. That was called Pundai Project and was completed in February 1992. Technology. In the public imagination, maglev often evokes the concept of an elevated monorail track with a linear motor. This can be misleading. While several maglev systems are monorail designs, not all maglevs use monorails, and not all monorail trains use linear motors or magnetic levitation. Some railway transport systems incorporate linear motors but only use electromagnetism for propulsion, without actually levitating the vehicle. Such trains are wheeled vehicles and not maglev trains. Maglev tracks, monorail or not, can also be constructed at grade. Conversely, non-maglev tracks, monorail or not, can be elevated too. Some maglev trains do incorporate wheels and function like linear motor-propelled wheeled vehicles at slower speeds but take off, and levitate at higher speeds. Overview. The term maglev refers not only to the vehicles, but to the railway system as well, specifically designed for magnetic levitation and propulsion. All operational implementations of maglev technology have had minimal overlap with wheeled train technology and have not been compatible with conventional rail tracks. Because they cannot share existing infrastructure, these maglev systems must be designed as complete transportation systems. The applied levitation SPM maglev system is interoperable with steel rail tracks and would permit maglev vehicles and conventional trains to operate at the same time on the same right-of-way. MAN in Germany also designed a maglev system that worked with conventional rails, but it was never fully developed. See also super-maglev technology, transrapid technology, magnetic levitation. There are 2 particularly notable types of maglev technology. For electromagnetic suspension, electronically controlled electromagnets in the train attract it to a magnetically conductive track. Electrodynamic suspension uses superconducting electromagnets or strong permanent magnets which create a magnetic field that induces currents in nearby metallic conductors when there is relative movement which pushes and pulls the train towards the designed levitation position on the guideway. Another experimental technology, which was designed, proven mathematically, peer-reviewed, and patented, but is yet to be built, is the magnetodynamic suspension, which uses the attractive magnetic force of a permanent magnet array near a steel track to lift the train and hold it in place. Other technologies such as repulsive permanent magnets and superconducting magnets have seen some research. Electromagnetic suspension. In current electromagnetic suspension systems, the train levitates above a steel rail while electromagnets, attached to the train, are oriented towards the rail from below. The system is typically arranged on a series of C-shaped arms, with the upper portion of the arm attached to the vehicle, and the lower inside edge containing the magnets. The rail is situated between the upper and lower edges. Magnetic attraction varies inversely with the cube of distance. so minor changes in distance between the magnets and the rail produce greatly varying forces. These changes in force are dynamically unstable. If there is a slight divergence from the optimum position, the tendency will be to exacerbate this, and complex systems of feedback control are required to maintain a train at a constant distance from the track. The major advantage to suspended maglev systems is that they work at all speeds, unlike electrodynamic systems which only work at a minimum speed of about 30 km/h. This eliminates the need for a separate low-speed suspension system, and can simplify the track layout as a result. On the downside, the dynamic instability of the system puts high demands on tolerance control of the track, which can offset, or eliminate this advantage. Levitate, highly skeptical of the concept, was concerned that in order to make a track with the required tolerances, the gap between the magnets and rail would have to be increased to the point where the magnets would be unreasonably large. In practice, this problem was addressed through increased performance of the feedback systems, which allow the system to run with close tolerances. Electrodynamic suspension. In electrodynamic suspension, both the guideway and the train exert a magnetic field, and the train is levitated by the repulsive and attractive force between these magnetic fields. In some configurations, the train can be levitated only by repulsive force. In the early stages of maglev development at the Miyazaki test track, a purely repulsive system was used instead of the later repulsive and attractive EDS system. There is a misconception that the EDS system is purely a repulsive one, but that is not true. The magnetic field in the train is produced by either superconducting magnets or by an array of permanent magnets. The repulsive and attractive force in the track is created by an induced magnetic field in wires or other conducting strips in the track. A major advantage of the EDS maglev systems is that they are naturally stable. A minor narrowing in distance between the track and the magnets creates strong forces to repel the magnets back to their original position, while a slight increase in distance greatly reduces the repulsive force and again returns the vehicle to the right separation. In addition, the attractive force varies in the opposite manner, providing the same adjustment effects. No feedback control is needed. EDS systems have a major downside as well. At slow speeds, the current induced in these coils and the resultant magnetic flux is not large enough to support the weight of the train. For this reason, the train must have wheels or some other form of landing gear to support the train until it reaches a speed that can sustain levitation. Since a train may stop at any location, due to equipment problems for instance, the entire track must be able to support both low-speed and high-speed operation. Another downside is that the EDS system naturally creates a field in the track in front and to the rear of the lift magnets, which acts against the magnets and creates a form of drag. This is generally only a concern at low speeds. At higher speeds the effect does not have time to build to its full potential and other forms of drag dominate. The drag force can be used to the electrodynamic system's advantage, however, as it creates a varying force in the rails that can be used as a reactionary system to drive the train, without the need for a separate reaction plate, as in most linear motor systems. Levitate led development of such transverse flux systems at his Imperial College laboratory. Alternatively, propulsion coils on the guideway are used to exert a force on the magnets in the train and make the train move forward. The propulsion coils that exert a force on the train are effectively a linear motor. An alternating current through the coils generates a continuously varying magnetic field that moves forward along the track. The frequency of the alternating current is synchronized to match the speed of the train. The offset between the field exerted by magnets on the train and the applied field creates a force moving the train forward. Pros and cons of different technologies. Each implementation of the magnetic levitation principle for train-type travel involves advantages and disadvantages. Neither inductrack nor the superconducting EDS are able to levitate vehicles at a standstill, although inductrack provides levitation down to a much lower speed. Wheels are required for these systems. EMS systems are wheel-less. The German Transrapid, Japanese HSST, and Korean Rotom EMS maglevs levitate at a standstill, with electricity extracted from guideway using power rails for the latter two, and wirelessly for transrapid. If guideway power is lost on the move, the transrapid is still able to generate levitation down to 10 km/h speed, using the power from board batteries. This is not the case with the HSST and ROTAM systems. Propulsion: some EMS systems such as HSST Linamo can provide both levitation and propulsion using an onboard linear motor. But EDS systems and some EMS systems such as Transrapid can only levitate the train using the magnets on board, not propel it forward. As such, vehicles need some other technology for propulsion. A linear motor mounted in the track is one solution. Over long distances the cost of propulsion coils could be prohibitive. Stability: Earnshaw's theorem shows that any combination of static magnets cannot be in a stable equilibrium. Therefore a dynamic magnetic field is required to achieve stabilization. EMS systems rely on active electronic stabilization which constantly measure the bearing distance and adjust the electromagnet current accordingly. All EDS systems rely on changing magnetic fields creating electrical currents, and these can give passive stability. Because maglev vehicles essentially fly, stabilization of pitch, roll and yaw is required by magnetic technology. In addition to rotation, surge, sway or heave can be problematic with some technologies. If superconducting magnets are used on a train above a track made out of a permanent magnet, then the train would be locked into its lateral position on the track. It can move linearly along the track, but not off the track. This is due to the Meissner effect and flux pinning. Guidance: some systems use null current systems. These use a coil which is wound so that it enters two opposing, alternating fields, so that the average flux in the loop is zero. When the vehicle is in the straight-ahead position, no current flows, but if it moves offline this creates a changing flux that generates a field that naturally pushes and pulls it back into line. Evacuated tubes: some systems propose the use of Vactrans-maglev train technology used in evacuated tubes, which removes air drag. This has the potential to increase speed and efficiency greatly, as most of the energy for conventional maglev trains is lost to aerodynamic drag. One potential risk for passengers of trains operating in evacuated tubes is that they could be exposed to the risk of cabin depressurization unless tunnel safety monitoring systems can repressurize the tube in the event of a train malfunction or accident. The RAND Corporation has depicted a vacuum tube train that could, in theory, cross the Atlantic or the USA in 21 minutes. Power and energy usage: energy from maglev trains is used to accelerate the train, and may be regained when the train slows down. It is also used to make the train levitate and to stabilize the movement of the train. The main part of the energy is needed to force the train through the air. Also some energy is used for air conditioning, heating, lighting and other miscellaneous systems. At low speeds the percentage of power used for levitation can be significant, consuming up to 15% more power than a subway or light rail service. Also for very short distances the energy used for acceleration might be considerable. But the power used to overcome air drag increases with the cube of the velocity, and hence dominates at high speed. Comparison with conventional trains: maglev transport is non-contact, electric-powered. It does not rely on the wheels, bearings and axles common to mechanical friction-reliant rail systems. Speeds: maglev allows higher top speeds than conventional rail, but at least experimentally, wheel-based high-speed trains have been able to demonstrate similar speeds. Maintenance requirements of electronic versus mechanical systems: maglev trains currently in operation have demonstrated the need for nearly insignificant guideway maintenance. Their electronic vehicle maintenance is minimal and more closely aligned with aircraft maintenance schedules based on hours of operation, rather than on speed or distance traveled. Traditional rail is subject to the wear and tear of miles of friction on mechanical systems and increases exponentially with speed, unlike maglev systems. The running costs difference is a cost advantage of maglev over rail and also directly affects system reliability, availability and sustainability. All-weather operations: while maglev trains currently in operation are not stopped, slowed, or have their schedules affected by snow, ice, severe cold, rain or high winds, they have not been operated in the wide range of conditions that traditional friction-based rail systems have operated. Maglev vehicles accelerate and decelerate faster than mechanical systems regardless of the slickness of the guideway or the slope of the grade because they are non-contact systems. Backwards compatibility: maglev trains currently in operation are not compatible with conventional track, and therefore require all new infrastructure for their entire route, but this is not a negative if high levels of reliability and low operational costs are the goal. By contrast, conventional high-speed trains such as the TGV are able to run at reduced speeds on existing rail infrastructure, thus reducing expenditure where new infrastructure would be particularly expensive, or on extensions where traffic does not justify new infrastructure. However, this shared track approach ignores mechanical rail's high maintenance requirements, costs and disruptions to travel from periodic maintenance on these existing lines. It is claimed by maglev advocates, most notably, Dr. John Harding, former chief maglev scientist at the Federal Railroad Administration, that the use of a completely separate maglev infrastructure more than pays for itself with dramatically higher levels of all-weather operational reliability and almost insignificant maintenance costs, but these claims have yet to be proven in an operational setting as intense as many traditional rail operations, and ignore the difference in maglev and traditional rail initial construction costs. So, maglev advocates would argue against rail backward compatibility and its concomitant high maintenance needs and costs. Efficiency: conventional railway is probably more efficient at lower speeds. But due to the lack of physical contact between the track and the vehicle, maglev trains experience no rolling resistance, leaving only air resistance and electromagnetic drag, potentially improving power efficiency. Some systems, however, such as the Central Japan Railway Company's super-maglev, use rubber tires at low speeds. Weight: the weight of the electromagnets in many EMS and EDS designs seems like a major design issue to the uninitiated. A strong magnetic field is required to levitate a maglev vehicle. For the Transrapid, this is between 1 and 2 kilowatts per ton. Another path for levitation is the use of superconductor magnets to reduce the energy consumption of the electromagnets, and the cost of maintaining the field. However, a 50-ton Transrapid maglev vehicle can lift an additional 20 tons, for a total of 70 tons, which consumes between 70 and 140 a kilowatt. Most energy use for the TRI is for propulsion and overcoming the friction of air resistance at speeds over 100 mph. Weight loading: high-speed locomotives requires more support and construction for its concentrated wheel loading. Maglevs, on the other hand, is not only lighter than its conventional counterparts, its weight is also more evenly distributed. Noise: because the major source of noise of a maglev train comes from displaced air, maglev trains produce less noise than a conventional train at equivalent speeds. However, the psychoacoustic profile of the maglev may reduce this benefit. A study concluded that maglev noise should be rated like road traffic, while conventional trains have a €5 decibels bonus as they are found less annoying at the same loudness level. Design comparisons: braking and overhead wire wear have caused problems for the Fastech 360 railed Shinkansen. Maglev would eliminate these issues. Magnet reliability at higher temperatures is a countervailing comparative disadvantage, but new alloys and manufacturing techniques have resulted in magnets that maintain their levitational force at higher temperatures. Control systems: there are no signaling systems for high or low-speed maglev systems. There is no need since all these systems are computer-controlled. Besides, at the extremely high speeds of these systems, no human operator could react fast enough to slow down or stop in time. This is also why these systems require dedicated rights-of-way and are usually proposed to be elevated several meters above ground level. Two maglev system microwave towers are in contact with an EMS vehicle at all times for two-way communication between the vehicle and the Central Command Center's main operations computer. There are no need for train whistles or horns either. Lower gradient: maglevs are able to ascend higher grades as compared with its conventional counterparts. It means less tunneling through mountains and ability to achieve more direct routing. Comparison with aircraft: although maglev and aircraft both are very similar as operation, there are some significant differences. Efficiency for many systems: it is possible to define a lift-to-drag ratio. For maglev systems, these ratios can exceed that of aircraft. This can make maglev more efficient per kilometer. However, at high cruising speeds, aerodynamic drag is much larger than lift-induced drag. Jet transport aircraft take advantage of low air density at high altitudes to significantly reduce drag during cruise, hence despite their lift-to-drag ratio disadvantage, they can travel more efficiently at high speeds than maglev trains that operate at sea level. Flexibility and reliability. While aircraft are theoretically more flexible, commercial air routes are not. High-speed maglevs are designed to compete on journey times with flights of 800 kilometers or less. Additionally, while maglevs can serve several cities in between such routes and be on time in all weather conditions, airlines cannot come close to such reliability or performance. Cost of travel. Because maglev vehicles are powered by electricity and do not carry fuel, maglev fares are less susceptible to the volatile price swings created by oil markets. Traveling via maglev also offers a significant safety margin over air travel since maglevs are designed not to crash into other maglevs or leave their guideways. Aircraft fuel is a significant danger during takeoff and landing accidents. Travel time. In real-world situations, the speed of maglev are less than aircraft, but maglev still save time due to minimal hassles it takes to travel in them as compared to air travel. With air travel, people need to spend time at airports for check-in, security, boarding, etc. In air travel, time is also consumed by the aircraft for taxiing, waiting in queue for takeoff and landing, which are negligible in case of maglev. Economics. The Shanghai maglev demonstration line cost $1.2 billion to build. This total includes infrastructure capital costs such as right-of-way clearing, extensive pile driving, on-site guideway manufacturing, in-situ pier construction every 25 meters, a maintenance facility and vehicle yard, several switches, 2 stations, operations and control systems, power feed system, cables and inverters, and operational training. Ridership is not a primary focus of this demonstration line, since the Longyang Road station is on the eastern outskirts of Shanghai. Once the line is extended to South Shanghai Train Station and Henglai Airport Station, ridership will be ample enough for the SMT to not only cover operation and maintenance costs, which it already does with its demonstration leg, but it will be able to generate significant revenue. When the SMT in Shanghai begins to extend its line to South Shanghai Train Station, its goal is to limit the cost of future construction to approximately $18 a million per kilometer. They are confident about this since the German government, in 2006, put $125 a million into guideway cost reduction development, which resulted in an all-concrete modular guideway design that is faster to build and is more than 30% less costly than what was used in Shanghai. In addition, new construction techniques were also developed that now put maglev at price parity with new high-speed rail construction, or even less. The United States Federal Railroad Administration 2003 draft environmental impact statement for a proposed Baltimore-Washington maglev project gives an estimated 2008 capital costs of $4.361 billion for 39.1 miles, or $111.5 a million per mile. The Maryland Transit Administration conducted their own environmental impact statement, and put the price tag at $4.9 a billion for construction, and $53 a million a year for operations. The proposed Chuo Shinkansen maglev in Japan is estimated to cost approximately $82 a billion to build, with a route blasting long tunnels through mountains. A Tokaido maglev route replacing the current Shinkansen would cost some 1/10 the cost, as no new tunnel blasting would be needed, but noise pollution issues would make it infeasible. The only low-speed maglev currently operational, the Japanese Linamo HSST, cost approximately $100 a million km to build. Besides offering improved operation and maintenance costs over other transit systems, these low-speed maglevs provide ultra-high levels of operational reliability and introduce little noise and zero air pollution into dense urban settings. As maglev systems are deployed around the world, experts expect construction costs to drop as new construction methods are innovated along with economies of scale. records, the highest recorded speed of a maglev train is 581 km/h, achieved in Japan by Junior Central's MLX-01 superconducting maglev in 2003, 6 km/h faster than the conventional TGV wheel rail speed record. However, the operational and performance differences between these two very different technologies is far greater than a mere 6 km/h of speed. For example, the TGV record was achieved accelerating down a 72.4 km slight incline, requiring 13 minutes. It then took another 77.25 km for the TGV to stop, requiring a total distance of 149.65 km for the test. The MLX-01 record, however, was achieved on the 18.4 km Yamanashi test track Euro 1/8, the distance needed for the TGV test. While it is claimed high-speed maglevs can actually operate commercially at these speeds while wheel rail trains cannot, and do so without the burden and expense of extensive maintenance, no maglev or wheel rail commercial operation has actually been attempted at these speeds over 500 km/h. History of maglev speed records: 1971 Euro West Germany Euro Prinzenzug Euro 90 km/h, 1971 Euro West Germany Euro TRO2 Euro 164 km/h, 1972 Euro Japan Euro ML 100 Euro 60 km/h Euro, 1973 Euro West Germany Euro TRO4 Euro 250 km/h, 1974 Euro West Germany Euro EETO1 Euro 230 km/h, 1975 Euro West Germany Euro Comet Euro 401 km/h, 1978 Euro Japan Euro HSSTO1 Euro 308 km/h, 1978 Euro Japan Euro HSSTO2 Euro 110 km/h, December 12, 1979 Euro Japan ML 500RA Euro 504 km/h. It succeeds in operation over 500 km/h for the first time in the world. December 21, 1979 Euro Japan ML 500RA Euro 517 km/h, 1987 Euro West Germany Euro TRO6 Euro 406 km/h, 1987 Euro Japan Euro MLU001 Euro 401 km/h, 1988 Euro West Germany Euro TRO6 Euro 413 km/h, 1989 Euro West Germany Euro TRO7 Euro 436 km/h, 1993 Euro Germany Euro TRO7 Euro 450 km/h, 1994 Euro Japan Euro MLU002NA Euro 431 km/h, 1997 Euro Japan Euro MLX-01 Euro 531 km/h, 1997 Euro Japan Euro MLX-01 Euro 550 km/h, 1999 Euro Japan Euro MLX-01 Euro 552 km/h. Guinness authorization. 2003 Euro China Euro Transrapid Summit Euro 501 km/h, 2003 Euro China Euro Transrapid Summit 476 km/h, 2003 Euro Japan Euro MLX-01 Euro 581 km/h. Guinness authorization. Existing maglev systems, testing tracks, San Diego, USA. General Atomics has a 120-meter test facility in San Diego, which is being used as the basis of Union Pacific's 8 km freight shuttle in Los Angeles. The technology is passive, using permanent magnets in a hull-back array for lift, and requiring no electromagnets for either levitation or propulsion. General Atomics has received $90 million in research funding from the federal government. They are also looking to apply their technology to high-speed passenger services. Super-maglev, Japan. Japan has a demonstration line in Yamanashi Prefecture where test trains super-maglev MLX-01 have reached 581 km/h, slightly faster than any wheeled trains. These trains use superconducting magnets which allow for a larger gap, and repulsive attractive type electrodynamic suspension. In comparison, transrapid uses conventional electromagnets and attractive-type electromagnetic suspension. These superconducting maglev Shinkansen, developed by the Central Japan Railway Company and Kawasaki Heavy Industries, are currently the fastest trains in the world, achieving a record speed of 581 km/h on December 2, 2003. FTA's UMTD program, in the U.S., the Federal Transit Administration Urban Maglev Technology Demonstration Program has funded the design of several low-speed urban maglev demonstration projects. It has assessed HSST for the Maryland Department of Transportation and maglev technology for the Colorado Department of Transportation. The FTA has also funded work by General Atomics at California University of Pennsylvania to demonstrate new maglev designs, the MAN Motion M3 and of the Maglev 2000 of Florida's superconducting EDS system. Other U.S. urban maglev demonstration projects of note are the LEVX in Washington State and the Massachusetts-based MagPlane. Southwest Jiaotong University, China, on December 31, 2000, the first crewed high-temperature superconducting maglev was tested successfully at Southwest Jiaotong University, Xiongde, China. This system is based on the principle that bulk high-temperature superconductors can be levitated or suspended stably above or below a permanent magnet. The load was over 530 kg and the levitation gap over 20 ohm. The system uses liquid nitrogen, which is very cheap, to cool the superconductor. Operational systems serving the public, Shanghai Maglev. In January 2001, the Chinese signed an agreement with the German maglev consortium Transrapid to build an EMS high-speed maglev line to link Pudong International Airport with Longyang Road Metro Station on the eastern edge of Shanghai. This Shanghai maglev train demonstration line, or initial operating segment, has been in commercial operation since April 2004 and now operates 115 daily trips that traverse the 30 km between the two stations in just 7 minutes, achieving a top speed of 431 km/h, averaging 266 km/h. On a November 12, 2003 system commissioning test run, the Shanghai maglev achieved a speed of 501 km/h, which is its design top cruising speed for longer intercity routes. Unlike the old Birmingham maglev technology, the Shanghai maglev is extremely fast and comes with on-time Euro to the second Euro reliability of greater than 99.97%. Plans to extend the line to Shanghai South Railway Station and Henglai Airport on the western edge of Shanghai have been put on hold. After the Shanghai Euro-Hanzhou passenger railway has become operational in late 2010, the maglev extension has become somewhat redundant and may be cancelled. Linamo. The commercial automated urban maglev system commenced operation in March 2005 in Agi, Japan. This is the 9-station 9 km long Tobukuro line, otherwise known as the Linamo. The line has a minimum operating radius of 75 am and a maximum gradient of 6%. The linear motor magnetically levitated train has a top speed of 100 km/h. More than 10 million passengers used this urban maglev line in its first 3 months of operation. At 100 km/h, this urban transit technology is sufficiently fast for frequent stops, has little or no noise impact on surrounding communities, can fit into tight turn radii rights of way, and will operate reliably during most inclement weather conditions. The trains were designed by the Shubu HSST Development Corporation, which also operates a test track in Nagoya. Daejeon, South Korea. The first maglev using electromagnetic suspension open to public was HML03, made by Hyundai Heavy Industries for the Daejeon Expo in 1993, after 5 years of research and manufacturing 2 prototypes, HML01 and HML02. Research for urban maglev using electromagnetic suspension began in 1994 by the government. The first urban maglev open to public was UTM-02 in Daejeon on April 21, 2008 after 14 years of development and building one prototype. UTM-01. The urban maglev runs on a 1 km track between Expo Park and National Science Museum. Meanwhile, UTM-02 remarked an innovation by conducting the world's first ever maglev simulation. However, UTM-02 is still the second prototype of a final model. The final UTM model of Rotem's urban maglev, UTM-03, is scheduled to debut at the end of 2013 in Incheon's Yongjong Island, where Incheon International Airport is located. Under construction, Old Dominion University. In 1999, Old Dominion University in Virginia, USA, agreed to work with American Maglev Technologies of Atlanta to construct an on-campus student transportation link of less than 1 mile using a smart train/dump track design in which most sensors, magnets, and computation were located on the train rather than the track. With cost and safety concern, several other institutes of higher learning rejected the project. While projected to cost less to build per mile than existing systems, the ODU maglev was never operational. After depleting its $14 million budget, a groundbreaking was held in 2001, the project was completed in 2002. And the technology failed, the vehicle lost its float, and come to a full friction stop on top of the rail, damaging much of the system. American Maglev and ODU dissolved their relationship and the project became an internal university research project. In October 2006, the research team performed an unscheduled test of the car that went smoothly. The system was subsequently removed from the power grid for nearby construction. In February 2009, the team retested the sled and was successful despite power outages on campus. ODU subsequently partnered with a Massachusetts-based company to test another maglev train. MAN Motion Incorporated was expected to bring its prototype maglev vehicle, about the size of a van, to the campus to test in 2010. AMT Test Tracker Powder Springs, Georgia. The same principle is involved in the construction of a second prototype system in Powder Springs, Georgia, USA, by American Maglev Technology, Incorporated. The test track is 2,000 feet long with a 550 feet curve. Vehicles are operated up to 37 mph, which is below the proposed operational maximum of 60 mph. A June 2013 review of the technology called for an extensive testing program to be carried out to ensure the system complies with various regulatory requirements, including the American Society of Civil Engineers APM standard. The review noted that the test track is too short to assess the vehicle's dynamics at the maximum proposed speeds. Applied Levitation Fast Transit Test Tracker Santa Barbara, California. Applied Levitation, Incorporated has built a levitating prototype on a short indoor track, and is now planning a quarter-mile outdoor track, with switches, in or near Santa Barbara. Beijing S1 Line. The Beijing municipal government is building China's first low-speed maglev line, the Line S1, BCR, using technology developed by Defense Technology University. This is the 10.2 km long S1 West commuter rail line, which, together with 7 other conventional lines, saw construction begin on February 28, 2011. The top speed will be 105 km/h. This problem is scheduled to be completed in 2015. Incheon Airport Maglev. At Incheon Airport, South Korea, directly above Incheon International Airport Station, is the upcoming Incheon Airport Maglev. When the first of 3 planned phases opens, it will be 6.1 kilometers long, with 6 stations and a 110 km/h operating speed. Opening is set for early 2014. Proposed systems. Many maglev systems have been proposed in various nations of North America, Asia, and Europe. Many are still in the early planning stages, or even mere speculation, as with the transatlantic tunnel. But a few of the following examples have progressed beyond that point. Australia, Sydney Illawarra maglev proposal. There is a current proposal for a maglev route between Sydney and Wollongong. The proposal came to prominence in the mid-1990s. The Sydney-Wollongong commuter corridor is the largest in Australia, with upwards of 20,000 people commuting from the Illawarra to Sydney for work each day. Current trains crawl along the dated Illawarra line, between the cliff face of the Illawarra escarpment and the Pacific Ocean, with travel times about 2 hours between Wollongong Station and Central. The proposed maglev would cut travel times to 20 minutes. Melbourne maglev proposal. In late 2008, a proposal was put forward to the government of Victoria to build a privately funded and operated maglev line to service the Greater Melbourne metropolitan area in response to the Eddington Transport Report, which neglected to investigate above-ground transport options. The maglev would service a population of over 4 million, and the proposal was costed at $8 a billion. However, despite relentless road congestion and the highest road space per capita in Australia, the government quickly dismissed the proposal in favour of road expansion, including an $8.5 a billion road tunnel, $6 a billion extension of the EASA link to the Western Ring Road, and a $700 a million Frankston bypass. United Kingdom. London Glasgow, a maglev line, described in a 2006 factbook, was proposed in the United Kingdom from London to Glasgow with several route options through the Midlands, northwest and northeast of England, and was reported to be under favourable consideration by the government. But the technology was rejected for future planning in the government white paper Delivering a Sustainable Railway, published on July 24, 2007. Another high-speed link is being planned between Glasgow and Edinburgh, but there is no settled technology for it. United States, Union Pacific Freight Conveyor. Plans are underway by American railroad operator Union Pacific to build a 7.9 km container shuttle between the ports of Los Angeles and Long Beach, with UP's intermodal container transfer facility. The system would be based on passive technology, especially well suited to freight transfer as no power is needed on board, simply a chassis which glides to its destination. The system is being designed by General Atomics. California-Nevada Interstate Maglev. High-speed maglev lines between major cities of Southern California and Las Vegas are also being studied via the California-Nevada Interstate Maglev project. This plan was originally supposed to be part of an I-5 or I-15 expansion plan, but the federal government has ruled it must be separated from interstate public work projects. Since the federal government decision, private groups from Nevada have proposed a line running from Las Vegas to Los Angeles with stops in Primm, Nevada, Baker, California, and points throughout San Bernardino County into Los Angeles. Southern California politicians have not been receptive to these proposals. Many are concerned that a high-speed rail line out of state would drive out dollars that would be spent in-state on a rail to Nevada. Baltimore-Washington D.C. maglev. A 64 km project has been proposed linking Camden Yards and Baltimore-Washington International Airport to Union Station in Washington, D.C. It is said to be in demand for the area due to its current traffic congestion problems. The Pennsylvania Project. The Pennsylvania High-Speed Maglev Project corridor extends from the Pittsburgh International Airport to Greensburg, with intermediate stops in downtown Pittsburgh and Monroeville. This initial project will serve a population of approximately 2.4 million people in the Pittsburgh metropolitan area. The Baltimore proposal is competing with the Pittsburgh proposal for a $90 a million federal grant. The purpose of the project is to see if the maglev system can function properly in a U.S. city environment. San Diego Imperial County Airport. In 2006, San Diego commissioned a study for a maglev line to a proposed airport located in Imperial County. SANDAG says that the concept would be an airports without terminals, allowing passengers to check in at a terminal in San Diego and take the maglev to Imperial Airport and board the airplane there as if they went directly through the terminal in the Imperial location. In addition, the maglev would have the potential to carry high-priority freight. Further studies have been requested although no funding has yet been agreed. Orlando International Airport to Orange County Convention Center. In December 2012, the Florida Department of Transportation gave conditional approval to a proposal by American Maglev to build a privately run 14.9-mile, 5-station line from the Orlando International Airport to the Orange County Convention Center. The department requested a technical assessment of the technology and said there would be a request for proposals issued to see if there are any competing plans. The route requires the use of a public right-of-way. If the first phase is successful, American Maglev would propose extensions in 2 further phases to carry the line to Walt Disney World. Puerto Rico, San Juan Caguas. A 16.7-mile maglev project has been proposed linking Tren Urbanos QP station in San Juan with two proposed stations to be built in the city of Caguas, south of San Juan. The maglev line would run along Highway Prairie 52, connecting both cities. According to American Maglev Technology, which is the company in charge of the construction of this train, the cost of the project is approximately $380 a million for one track connecting both cities. Germany. On September 25, 2007, Bavaria announced it would build a high-speed maglev rail service from the city of Munich to its airport. The Bavarian government signed contracts with Deutsche Bahn and Transrapid with Siemens and ThyssenKrupp for the $1.85 billion project. On March 27, 2008, the German transport minister announced the project had been cancelled due to rising costs associated with constructing the track. A new estimate put the project between a €3.4 billion. Switzerland. Swiss Rapide. The Swiss Rapide AG together with the Swiss Rapide Consortium is planning and developing the first maglev monorail system for intercity traffic between major cities in the country. The Swiss Rapide Express is an innovative solution for the coming transportation challenges in Switzerland. As pioneer for large infrastructure projects, Swiss Rapide is to be financed to 100% by private investors. In the long term, the Swiss Rapide Express is to connect the major cities north of the Alps between Geneva and St. Gallen, including Lucerne and Basel. The first projects currently in planning are Bern-Zurich, Lausanne-Geneva as well as Zurich-Winterthur. The first line could go into service as early as 2020. Swiss Metro, an earlier project, Swiss Metro, has previously attempted to provide a solution for the transportation challenges in the country. The Swiss Metro AG had the technically challenging vision of constructing an underground maglev rail system, which would have been in a partial vacuum in order to reduce air friction at high speeds. As with Swiss Rapide, Swiss Metro envisioned connecting the major cities in Switzerland with one another. In 2011, Swiss Metro AG was dissolved and the IPRs from the organization were passed on to the EPFL in Lausanne. Japan, Tokyo Nagoya Osaka. The plan for the Chuo Shinkansen bullet train system was finalized based on the law for construction of country-wide Shinkansen. The linear Chuo Shinkansen project aims to realize this plan using the superconductive magnetically levitated train, which connects Tokyo and Osaka by way of Nagoya, the capital city of Aichi, in approximately 1 hour at a speed of 500 km/h. In April 2007, Junior Central President Masayuki Matsumoto said that Junior Central aims to begin commercial maglev service between Tokyo and Nagoya in the year 2025 with the full track between Tokyo and Osaka finalized in 2045. China, Shanghai Hanzhou. China is planning to extend the existing Shanghai maglev train, initially by some 35 km to Shanghai Henglai Airport and then 200 km to the city of Hanzhou. If built, this would be the first intercity maglev rail line in commercial service. The project has been controversial and repeatedly delayed. In May 2007 the project was suspended by officials, reportedly due to public concerns about radiation from the maglev system. In January and February 2008 hundreds of residents demonstrated in downtown Shanghai against the line being built too close to their homes, citing concerns about sickness due to exposure to the strong magnetic field, noise, pollution and devaluation of property near to the lines. Final approval to build the line was granted on August 18, 2008. Originally scheduled to be ready by Expo 2010, current plans call for completion by 2014. The Shanghai municipal government has considered multiple options, including building the line underground to allay the public's fear of electromagnetic pollution. This same report states that the final decision has to be approved by the National Development and Reform Commission. The Shanghai municipal government may also build a factory in Nanhui district to produce low-speed maglev trains for urban use. Changsha. The Hunan provincial government has plans to construct a maglev line between Changsha Huanghe International Airport and Changsha South Railway Station. Construction work is expected to start in May 2014, and to be completed by the end of 2015. India, Mumbai Delhi, a maglev line project was presented to the Indian Railway Minister by an American company. A line was proposed to serve between the cities of Mumbai and Delhi. The Prime Minister Manmohan Singh said that if the line project is successful, the Indian government would build lines between other cities and also between Mumbai Central and Chhatrapati Shivaji International Airport Mumbai-Nagpur. The state of Maharashtra has also approved a feasibility study for a maglev train between Mumbai and Nagpur about 1,000 km away. It plans to connect the regions of Mumbai and Pune with Nagpur via less developed hinterland. Chennai Bangalore Mysore, Large and Medium-Scale Industries Minister of Karnataka Mr. Murajesh Nirani, a detailed report will be prepared and submitted by December 2012 and the project is expected to cost $26 million per kilometer of railway track. The speed of maglev will be 350 km per hour and will take 1 hour 30 minutes from Chennai to Mysore via Bangalore. Malaysia, a consortium led by UEM Group BHD and ARA Group, has proposed to use maglev technology linking across cities in Malaysia to Singapore. This will be a boost to business to compete against neighbouring country, Singapore. The idea first mooted by the YTL Group. Its technology partner then was said to be Germania unregistered trademark S. Siemens, but proposal however did not get the green light, due in part to the high costs involved. But the concept of a high-speed rail link from KL to Singapore recently surfaced again. It was cited as a proposed high-impact project in the Economic Transformation Programme that was unveiled in 2010. The line would be connected from Penang Kuala Lumpur Singapore. It would take about 90 minutes from Singapore to Kuala Lumpur. Indonesia, there are plans to build a 683 km long maglev rail service between Jakarta and Surabaya. This maglev will have 7 stations including Semarang. Also there are plans to build a maglev rail service between Pontianak and Samarinda. Iran, in May 2009, Iran and a German company signed an agreement on using maglev trains to link the cities of Tehran and Mashhad. The agreement was signed at the Mashhad International Fair site between Iranian Ministry of Roads and Transportation and the German company. Maglev trains can reduce the 900 km travel time between Tehran and Mashhad to about 2.5 hours. Munich-based Schlegel Consulting Engineers said they had signed the contract with the Iranian Ministry of Transport and the governor of Mashhad. "We have been mandated to lead a German consortium in this project," a spokesman said. "We are in a preparatory phase. The next step will be assemble a consortium, a process that is expected to take place in the coming months," the spokesman said. The project could be worth between 10 billion and 12 billion euros, the Schlegel spokesman said. Siemens and ThyssenKrupp, the developers of a high-speed maglev train called the Transrapid, both said they were unaware of the proposal. The Schlegel spokesman said Siemens and ThyssenKrupp were currently not involved. In the consortium, significant incidents, there have been 2 incidents involving fires. The Japanese test train in Miyazaki, MLU-002, was completely consumed in a fire in 1991. As a result of the fire, political opposition in Japan claimed maglev was a waste of public money. On August 11, 2006, a fire broke out on the commercial Shanghai Transrapid shortly after arriving at the Longyang terminal. People were quickly evacuated without incident before the vehicle was moved down line about 1 kilometer to avoid smoke filling the station. NAMTI officials toured the SMT maintenance facility in November 2010 and learned that the cause of the battery fire was thermal runaway in one of the battery trays. As a result of these findings, SMT secured a new battery vendor, installed new temperature sensors and insulators, and redesigned the battery trays to prevent a reoccurrence of the event. Template, Kevin C. Coates. On September 22, 2006, a Transrapid train collided with a maintenance vehicle on a test publicity run in Lathan. 23 people were killed and 10 were injured. These were the first fatalities resulting from an accident on a maglev system. The accident was caused by human error. Charges were brought against 3 Transrapid employees after a year-long investigation. See also. Notes. Further reading. External links. Maglev 2000, North American Maglev Transport Institute, International Maglev Charter and Petition, Urban Maglev, Windana Research, United States Federal Railroad Administration, U.S. Magnetic Glide, Information Note on U.S. Maglev, Longer Information Note on U.S. Maglev, America needs a national magnetic levitated network. James Jordan, The International Maglev Board. Maglev Professionals Info Platform for all Maglev transport systems and related technologies. Applied Levitation, Fast Transit, Maglev Net. Maglev News and Information, Transrapid, the UK Ultra Speed Project, Japanese Railway Technical Research Institute, Magnetic Levitation at DMOZ, AMNAV MDS System, Magnetic Levitation for Transportation, News of Brazil's Maglev Project, Maglev Trains. Audio slideshow from the National High Magnetic Field Laboratory discusses magnetic levitation, the Meissner effect, magnetic flux trapping and superconductivity.